A fully loaded Boeing 747 weighs up to 412,000 kilograms at takeoff. That is heavier than 60 fully grown African elephants. And yet it lifts off the ground, climbs to 35,000 feet, and stays there for 14 hours straight. Most people think they know why. The wing is curved on top, flat on the bottom, air moves faster over the top, pressure drops, and the wing gets sucked upward. Simple. That explanation is actually wrong, or at least dangerously incomplete, and the real answer involves something far more interesting than a pressure difference. Before anything else, you need to understand that flight is not one force working in isolation. It is four forces in constant competition with each other, and the aircraft survives only as long as two specific pairs stay perfectly balanced. Weight pulls the aircraft straight down. Gravity does not care how big the engines are. On a 747 at maximum takeoff weight, that is over 400 tons pressing toward the ground every single second. Thrust pushes the aircraft forward. The 747 carries 4 high-bypass turbofan engines, each producing roughly 60,000 pounds of force. Their only job in cruise is to overcome drag, the resistance the air creates as the aircraft pushes through it. At 900 kilometers per hour, drag is a serious force. Without constant thrust, the aircraft slows, loses the ability to generate lift, and descends. That leaves lift, and this is where the real engineering begins. Because generating enough upward force to hold 412,000 kilograms in the air is not simple. It requires a combination of physics principles working simultaneously, and getting any one of them wrong is the difference between flight and catastrophe. So why is the common explanation really wrong? The version most people learned in school is called the equal transit time theory. The idea is that air molecules separating at the wing's leading edge must reunite at the trailing edge at the same moment. Because the upper surface is longer, those molecules must travel faster, which reduces pressure, which creates lift. NASA has explicitly flagged this as incorrect. Air molecules traveling over the top of a wing actually arrive at the trailing edge significantly earlier than those on the bottom. They do not travel at the speed required to produce equal transit time. In fact, the real velocity over the upper surface is far higher than that theory predicts, which is why the theory consistently underestimates how much lift a wing actually produces. The correct explanation requires both of the major physics principles working together, not just one. How did these flying elephants create lift? The wing shape does matter, but not for the reason most people think. The curved upper surface forces the airflow to follow a curved path. That curving requires a pressure difference to sustain it. The air above the wing is at lower pressure than the air below it. That pressure difference is real and it does contribute to lift, but it is only part of the story. The other part comes from the wing's angle of attack. Every wing in flight is tilted slightly upward relative to the oncoming air. As the air flows past, the wing redirects it downward. According to Newton's third law, if the wing pushes air down, the air pushes the wing up with equal force. That reaction force is the second major contributor to lift, and on a large transport aircraft at high angles of attack, it is enormous. The critical insight is this: both effects are inseparable. You cannot have one without the other. The pressure difference and the downward deflection of air are two descriptions of the same physical event. Together, they produce the upward force that keeps 400 tons in the air. And the magnitude of that force depends on a precise equation. Lift equals 1/2 times air density times velocity squared times wing area times the lift coefficient. Every variable matters critically, and changing any one of them changes everything. And that lift equation has one variable that controls everything. Notice that velocity appears in the lift equation as a square. That is not a minor detail. It means if you double the airspeed, lift does not double, it quadruples. And this relationship is what makes takeoff possible and what makes stalling so dangerous. A 747 requires a takeoff speed of roughly 290 to 300 kilometers per hour before the wings generate enough lift to match the aircraft's weight. Below that speed, no amount of wing curvature or angle of attack is sufficient to get 400 tons off the ground. The aircraft accelerates down the runway not because it is trying to jump, but because it needs to reach the velocity at which the lift equation tips in its favor. When that moment arrives, the wheels leave the ground on their own. No command is issued. The physics simply take over. But here's what makes it even more engineered than it sounds. At low speeds, the wings alone are not enough. That is why you have seen those massive mechanical structures deploying from the leading and trailing edges of wings on approach and takeoff. They are called flaps and slats, and their function is to physically transform the wing into a different shape. The 747's wing system is one of the most complex high-lift mechanisms ever built for a commercial aircraft. When the flaps are fully deployed, wing area increases by 21% and total lift capacity increases by 90% compared to the clean wing configuration. That is not a minor adjustment. It is a near total transformation of what the wing is physically capable of. The leading edge uses Kruger flaps that hinge forward from the underside of the wing, increasing camber and preventing stall at low speeds. The trailing edge deploys a complex 3-part slotted flap system. Each slot allows high-pressure air from below the wing to flow through a carefully shaped gap, re-energizing the boundary layer on the upper surface and delaying the stall that would otherwise occur. This entire system exists to solve one fundamental problem. The wing that works efficiently at 900 km per hour in cruise cannot generate enough lift at 250 km per hour for a safe landing. So engineers built a wing that literally reconfigures itself for each phase of flight. Subscribe if you want to understand exactly how the machines around you actually work. You would think these things would fly at a lower altitude than normal commercial flights, but you're wrong. Once airborne and climbing, something interesting happens. As the aircraft rises above 30,000 feet, the air becomes significantly thinner. Density drops by more than 70% compared to sea level. That means the same wing at the same speed generates far less lift in the lift equation. The aircraft compensates in two ways. First, it flies faster. At cruise altitude, a 747 travels at around 900 kilometers per hour, roughly Mach 0.85, generating the velocity squared lift component needed despite the thin air. Second, the angle of attack adjusts slightly upward. At 35,000 feet cruise, a 747 typically flies at around 2 to 3 degrees angle of attack, just enough to maintain level flight without excessive drag. But there is a benefit to the thin air as well. Less dense air means significantly less drag. That is why commercial aircraft do not fly at 10,000 feet. The fuel savings at high altitude are the entire economic basis of long-haul aviation. A 747 flying London to Sydney burns roughly 200,000 kilograms of fuel on that route. At lower altitude, that number would be catastrophically higher. There is something else happening at altitude that most people never consider. As the flight progresses and fuel burns off, the aircraft gets lighter. A 747 at the end of a long-haul flight can weigh 80 to 100 tons less than at departure. That means the wings need to generate less lift. Pilots handle this by executing what is called a step climb, gradually requesting higher altitudes from air traffic control as the aircraft lightens. Each step reduces drag, improves fuel efficiency, and keeps the operation economically viable. But the wing isn't infinitely adjustable. There's a point where physics simply refuses to cooperate. Every wing has a hard physical limit. As the angle of attack increases, lift increases up to a critical point. Beyond that point, the airflow over the upper surface can no longer follow the wing's contour. It separates. The smooth laminar flow becomes turbulent and chaotic. Lift drops suddenly and dramatically. This is a stall. For a 747 in cruise configuration, the critical angle of attack is around 15 to 18 degrees. The aircraft never approaches that in normal operation. But during low-speed flight with high-lift devices deployed, the margin between flying and stalling becomes much narrower. That is why speed is so carefully managed during approach and landing, and why auto-throttle systems exist to prevent pilots from inadvertently reducing speed below the minimum required to keep the wings effective. Now, to put everything we've talked about together, a 500-ton aircraft stays airborne because of the precise balance between 4 competing forces, managed continuously by the aircraft systems and the crew from the moment of takeoff to the moment the wheels touch down. The wing does not simply lift. It is a dynamic, reconfigurable aerodynamic machine that changes shape at different phases of flight to maintain that balance across an enormous range of speeds, weights, and altitudes. At 35,000 feet, cruising at 900 kilometers per hour, those 541 square meters of wing surface are generating a pressure differential smaller than you might expect, roughly equivalent to the weight of a small car distributed across each square meter, but spread across the entire wing that adds up to hundreds of tons of upward force, holding the aircraft exactly where it needs to be. Not because of magic, because the physics of moving air, engineered to an extraordinary degree of precision.